Now my computer's making the noise. We can even go to two-photon lithography, two-photon 3D printing, or nano-imprint lithography, all ways to make small structures. And we'll be looking at a couple of different ways of making membranes, starting off with microfabricated membranes. So here we can see a couple of holes that were made in a PDMS membrane. And so there was a template made by using positive structures, and these holes here in this case was a test piece, so the locations are not that important, but for the application they had in mind, they tried to microfabricate the pores in the areas they wanted to have pores in their assembled microfluidic device. And you can see by microfabrication we can make pores 10 micrometer, kind of still can see them at 4. Microfabrication techniques were actually kind of, anything under 10 is hard, anything under 5 is getting close to impossible. So making a membrane that will stop a virus like COVID, we just saw that we needed 50 nanometers. Using direct microfabrication, 50 nanometers is going to be a really hard thing to achieve. But larger membranes, if you want to separate organelles, want to be at that's up to 5 micron size based. If we just want to retain our cellular matter, microfabrication of membranes may actually be an option. Another thing instead of a membrane we could do is actually microfabricate a filter. So normally we know our filters, they are a crisscross thing of cellulose if it's a paper-based filter. You can also mimic that structure in a much more regular way by making pillars. Because if you would do solid phase extraction in this, for example, all these pillars add to the surface area that we've got available in our microchannel. The smaller the channels, the smaller the pillars, higher the surface area, the more effective it will be working as a chromatographic phase. And I know that there's some activities going on at the moment using two-photon lithography for printing chromatography columns, because you can really get very precise and accurate flow, because you can tailor a lot of your dispersion away through the way that you shape your pillars. So while a lot of our chromatography columns at the moment are either randomly synthesized polymer monoliths or silica monoliths, or they're beads with very random porous structure, the first people are working on microfabricated chromatography columns, because we lose a lot of that heterogeneity, which means that our bands get sharper. We can minimize one of our diffusion terms. Another alternative way of integrating membrane is not by fabricating them during the machining, but making them in situ. So making the membranes after we've made a device. An example here, we'll just go through them one by one. Under A, we'll go A. Here we've got a liquid membrane, which actually is not a membrane at all. What this is a device where we've got heptane flowing between 2 flows of water. And any lipophilic molecule that's in the water would quite happily enter and maybe even pass the lipophilic membrane. So there are supported liquid membranes. Sometimes they have pillars in there to keep them in place. In this case, it's just a fluidically stable system, perhaps stabilized with some surface functionalization. And the membrane here separating to 2 water phases is a liquid membrane. It's not a solid. So membranes don't necessarily have to be liquid. Under B, we've got a membrane being formed by the phase separation of acrylate monomers. So phase separation happens when the acrylate monomer is being formed in presence of a porogen, like in the synthesis of monoliths. So you can see that the microchannel initially is being filled with the pre-polymerization solution. There's no porous phase there, it's liquid. You hit it with UV light, we get the cross-linking to take place. The porogen does not participate in the cross-linking reaction. So we end up with a porous material here inside our microchannel without a lot of effort, because when we loaded the chip, we loaded it with liquid. So we could very easily get our liquid in place in our microfluidic device and then hit it with some UV light and do photo cross-linking. Very easy way of integrating functionality. Here we've got a polycondensation reaction. We've got a couple of chemists in the room. A lot of us will have worked on the synthesis of nylon, where we've got a two-phase reagent and the polymer forms where the two reagents are in contact. You can use that in microfluidics. You can flow your two reagents alongside each other. The reaction takes place at the interface. Exactly what the people have done in this paper here. So we had reagent A, reagent B, polymerization reaction happened at the interface, just like when you're making nylon. And here you can see an SEM where we have a membrane that's formed in our microchannel. Again, our reagents were liquid when they went in. It was an easy to handle process. Chemistry took care of the rest. So we synthetically, in situ, created a membrane, having reagents flowing in the different channels. One of the nice things I like about this picture that we can see is that they haven't quite balanced out the flows. You can see that the fluidic resistance here was a little bit lower than it was on that. No, I don't want to move. No, that's right. The fluidic resistance here was a little bit lower than it was here, or this pump was a little bit working a little bit harder. And you can see that the membrane, as a result, the interface was shifted a little bit. And because of that reason, our membrane is shifted a little bit as well. The last thing you can do, and that may be of interest of those of you that are studying biological membranes or doing some cell-based work, you can actually get membranes formed through self-assembly as well. So you can have a solution of phospholipids, and you can have a phospholipid bilayer being formed between two microfluidic chambers as well. And that way you can simulate a biological membrane by having structures that are close enough together so that the phospholipid bilayer is stable. And you can study transport processes across these structures. Once they're formed, they're quite stable. I've already spoken a little bit about polymer monoliths, and they're typically used as a stationary phase for chromatography. But I know we've got a couple of synthetic organic people here as well. So I want to make you aware that it's actually also possible to use these devices for synthetic chemistry. This is an outcome of a research project I had a couple of years ago, where we used polymer monoliths for heterogeneous catalysis. What we did is that we didn't even make them. We bought some micro devices, some microfluidic devices. Using a UV lamp, we made a polymer monolith in place that had an epoxide group on the. So we used GMA as one of the functional monomers, which has got an epoxide group, which allowed us to anchor phenanthrene on there. And phenanthrene could then coordinate palladium, so we could do palladium-based catalysis. So you can see here the polymer monolith, the phenanthrene ligand, and the coordination of palladium with the chloride in order to work as a heterogeneous catalyst. What we did is that we put the two reagents in, pumped it through a microreactor, and we did a Sodica-Shearer coupling, and we got carbon coupling, a palladium catalyzed carbon-carbon coupling reaction taking place in our flow-through microreactor. My contribution to that project was not that.
Yields are higher or lower?
Yields are higher, but harder to calculate because you do your synthesis as a batch, as a continuous process, and not as a batch. So it's a bit tricky to calculate, but the conversion rates are very close to 100%, even for the ones that are hard to convert. So we get very good conversion. The yields are good as well, but calculating the yield is a little bit tricky because it's not, I have 500 grams in my conical flask and this is how much I get out. The other thing that we found in that research project is that we get very little catalyst poisoning because it's a flow-through system. All unwanted products, eventually contaminants that could have come from the reagents, they're continuously washed away, which means that catalyst poisoning was much less of an issue in these flow-through catalysis systems than it was in the comparative bulk experiments that we did. And so some of the bits of the research we did was first a lot of optimization of the formulation to create the right porous properties of our solid support, because we wanted to have both high surface area, but also good flow properties, which means low fluidic resistance, so that our pump didn't have to work really hard. Here we can see traditionally, using the expensive way, a deep UV lamp is used for the cross-linking of the polymer monoliths, which is irradiating light at 260 nanometers. All the chromatography-based people make these in capillary columns, and you get a picture that looks like that. Chemistry-wise, the surface of borosilica chip is actually the same as a fused silica capillary. So you can see that if you put a chip, fill that with a pre-polymerization mixture, you get exactly the same thing. And if you get a UV transparent polymer, and this was a special grade of COC, you can see that in a polymer chip, you can form the same monolith as well. We played around with a UV LED array to make the synthesis and the making of these microreactors a little bit more accessible to all laboratories, because you're talking $60,000, I think, for the deep UV flood exposure source. The UV LED array was $300. So we have a significantly lower cost in our lamp. The price for us to pay is that that's a little bit lower intensity UV light, so we had to wait a little bit longer. But as you can see, with the UV LED array, we could also make our polymer monoliths in fused silica capillary, in glass microchannels, and in polymer microchannels. So it's a porous support. It has got high capacity. At that point, you're free to use it for catalysis or chromatography. The making of the support is not any different. Polymer monoliths have also been integrated by other people for other purposes. And here we've got a more advanced functionally integrated device for solid phase extraction. So you can see the gray area is here where they cross-linked the monolithic phase. They injected a sample, got the analyzed the target molecules that were in there adhering to the stationary phase. The ones that didn't have affinity didn't adhere, so they just washed out. Then rinsing step where you could check in the mass spectrometer what was going on or not, but the focused analytes were still sitting here. So the stationary phase could be washed from all contaminants, or at least a part of the stationary phase that was at our cross intersection. Then the background electrolyte came to first elute our compounds of interest into our separation channel, and then change the direction of the flow to inject into the mass spectrometer. And you can see that they were looking at a couple of different pharmaceuticals by mass spec, and they indeed could concentrate them and purify them and get a much clearer signal after cleanup with solid phase extraction on the microfluidic device than before. An even more advanced version is what we can see here. Again, it's a polymer monolith immobilized in a chip for solid phase extraction, and a CE separation device where they could do electrophoretic separation using pinched injection. So the idea here was that they were using the enriched phase eluding off the solid phase extraction column, that they used it here for pinched injection and then electrophoretic separation. Because solid phase extraction requires hydrodynamic flow, and they didn't want any crosstalk between the electrophoretic module and the solid phase extraction module, they integrated microfluidic valves to fluidically isolate the different parts of the assay. So when they were doing the solid phase extraction here, they have a couple of different fluid ports. They could get reagent in and out, but the valves that you can see sitting here around the injection cross, they were closed. So that means the CE system didn't do anything at all. And no contaminants from the solid phase extraction would end up in separation channel, because the solid phase extraction could be managed using the microchannels that are need to replicate the screens here. So solid phase extraction happened here, could load the sample, have a waste, do an elution. All the channels here were for the solid phase extraction. With the valve here closed, there was no interaction with our separation system, no contamination. And only once we opened the valves that are sitting here, it was possible to electrophoretically elute the solid phase extraction phase onto the intersection and then do a cross injection and a separation. So a much higher level of integration because we've got both the porous material, the stationary phase for solid phase extraction, and the valves here for fluidic control. One of the other papers that I really like is the work that I've done, in this case, in 3D printed microchannels. Again, after the making of the channels, introducing the polymer monoliths. In this case, Adam Wooley's group has applied this to preterm birth markers. Whilst all the monoliths look the same, they all like these cauliflower-like structures. What I wanted to already get in your mind before we go to 3D printing later this week is we can see this is a 3D printed device because we can see kind of this scalloped structure at the sides. 3D printing is a layer by layer technology. So we deposit one layer, we move up the stage, we deposit the next layer. You can see that every layer here by itself bulges out a bit, which means that we get this scalloped structure every layer that we print. And that's a defect of the printing. There's been some research being done to minimize that effect. Doesn't matter at all for the functionality of the assay that we're looking at here. You can see you can't see any of the layers. So the layers are perfectly adhered to one and each other. It becomes one material during the 3D printing process. But at the point where you've got the edge, you can see the scalloping structure, which is an artifact of the 3D printing process. But here we had 3D printed microchannels that were then, after the fact, filled with a pre-polymerization mixture. It was BACTA-based monolith, and they then functionalized that with antibodies for preterm birth markers, which is what we can see here. So here we've got the solid phase extraction, the monolith sitting here, the microfluidic and fluidic channels. So they could do solid phase extraction of markers in a pregnant woman's blood to see if they were at risk of giving preterm birth to their baby. And you can see here that with the loading, the Alexa fluor comes in, and with the rinse, there's still a very small amount specifically bound to the stationary phase, and then it can be eluted off. This worked quite well. So here you can see a whole range of different biomarkers, and usually in the laboratory, all of those are separate assays. You can see that they were quite well retained and eluted off the column with yields 60-70%. Other than here the difference, they were not. They clearly didn't have a very high affinity for the stationary phase being used. Fluorescence detection was used here. So the figure on the right is the figures of merit when using all the analytes spiked and pre-labeled. But they also managed to get an on-chip labeling step by passing the fluorescent reagents over this column. And here you can see the yields when doing on-chip labeling. There is a bit of a price to pay. There is a drop from around 80 to around 60 going to on-chip labeling, but it saves a lot of manual labor. And as you can see, the efficiencies for all the analytes are kind of similar because they're more like their native form by the time that they bind to the column. I realized there's a lot of work here going on molecular imprinted polymers, so I decided to also include an example on imprinting a molecular imprinted polymer for solid phase extraction on a microfluidic device. It also used an electrochemical detector, so that's why you can see here the microfabrication process included a step where they made the detection electrodes, and they created a molecular imprinted polymer by UV cross-linking post-fabrication of the device. So they made a device, then loaded the device from memory when it was still open. So before bonding, they deposited the polymerization mixture with the molecule to be imprinted. They used UV cross-linking to define the location on the device where they wanted their molecular imprinted polymer to be formed, and then sealed the device, which then allowed them to capture C-reactive protein was what they were measuring, using some surfactant in the elutant, and it then could be eluted down to the detection region for electrochemical detection. Another example to remind you that sometimes we have a problem with our macro to micro interfacing. And if we've got really, really large sample volumes with really low traces of our target analyte, it may actually not be worth the effort integrating your solid phase extraction onto your microfluidic device. You may be better off just packing a column to concentrate your analyte where you can have a large flow coming through, and then do your elution into a microfluidic device. Again, in this instance, using electrochemical detection on the sensor to detect glyphosate. So think about what your application is, think about the volumes that you're handling in every step. And sometimes it's just not practical to do your sample preparation on chip because you'd be waiting five days. Sometimes it may actually be more effective to have your affinity phase, which could be your molecular imprinted polymer, have it sitting in a little cartridge. This is just a small, I think it was a 1 milliliter syringe, where they put a frit at the bottom here, filter to make sure the molecular imprinted polymer didn't disappear. They could do the fluid handling of the sample, they could concentrate onto the syringe, then they put it onto the chip outlet. They got the eluent in there, they eluted the target analyte into a very small volume that then was introduced onto the microfluidic device for analysis. And so we've got a range of different ways of integrating porous materials, as we just seen, through in situ polymerization. There's also alternatives. We've got a lot of porous materials out there that are already optimized and are well known to serve as the best stationary phase for chromatography or solid phase extraction. We can use them as well in microfluidics. So we can either microfabricate weird-like structures where the particles can't get through. So we have a suspension of particles that we inject into a microchannel. We put a step in there using a two-layer process. The particles can only get to a certain point on the micro device, then they're blocked, and we can pack a column that way with commercially off-the-shelf particles. Similarly, we can use the keystone effect. The keystone effect is the fact that if the fire alarm now would go off and we all want to go out of that door, we will all be bunched up. Even though the door, none of us here is wider than the door. If a gap is 3 to 5 times wider than every single particle or person, you still get a traffic jam. And that's the keystone effect, and you can use that for particles as well. So if you've got 50 micron particles, if you taper your microchannel to be 150 wide, which is very feasible with most microfabrication technologies, the particles will actually block the channel and start packing into a column. And the last thing that I already told you this morning, it may also be possible to introduce a stationary phase before bonding. And then it's in there as well, depending or hoping that your bonding process is compatible with microfabrication. There's a lot of normal membrane fabrication methods as well that you can just buy off the shelf, just like the dialysis membranes. And we can use those membranes in microfluidic as well, simply by making them part of the microfabrication process. So we make the fluidic structure, put the membrane in place, we bond it. And in this way, this is an elastic membrane. Yeah. So you can do that with porous membrane. Any membrane that you can get off the shelf, you can actually make part of your microfluidic sandwich as well. And I told you, I showed you the work that we've done with the track edge membranes with the size mobility trap for the urine, where Fung had to cut these 1 by 2 millimeter little squares of membrane in order to have them as a part of our microfluidic structure. It is possible, so you can use the wealth of membranes that is available as well for integration. Keep in mind that the thinner the membrane is, the easier it is to integrate, because the less work you have to do to prevent leakage around the sites. And of course, with the porous materials, we also have the flexible membranes that we can use as valves. That's a part of membrane integration as well. Last integration of porous materials that I want to talk about is that you can actually also suspend hollow fiber modules in a microfluidic chamber. In this case, the fluidics was used to do it, to create a metal organic framework, having one reagent sitting out in the microfluidic flow chamber, which is in blue, one reagent sitting in the inside of the hollow fiber module, and we get the metal organic framework being formed where the two are in contact with one another. Next thing that... So what happens is that one reagent for making the MOF sits outside in the chamber.
Yeah.
The other one is pumped here through the inside. They come into contact here in this material, and that's where here the outside of the hollow, or the material that the hollow fiber is made of, starts to become coated with the metal organic framework. So here the reaction takes place and the material is being formed.
How much time of metal organic frameworks take a very long time for a formation?
I don't know, but the reference is here. So this is, I'll share the slides later. All the details in there, so I read it, it's quite well explained. I'm just not a metal organic framework person, but I knew you would like it. So the next thing is electrode integration, and we'll kind of be able to skip through that because we've already done a lot of electrode integration when we had our detection lecture. But again, it can be done during the microfabrication process, during the assembly, in situ synthesis, because there's ways that you can electrochemically make metals as well, or use conducting polymers, and post-fabrication, where we've got options including silver paint, assembly with screen printed electrodes for electrochemical detection. And there's new materials, a growing collection of new materials, including conducting polymers, and that can also be all adapted for microfabrication. So sputtering is the very oldest way of putting electrodes in, where you get a mask to protect most of your substrate and you sputter an electrode on top. And the very early work I did on conductivity detection, these platinum electrodes, initially there were little trenches being etched for them, and then the electrodes were selectively deposited using a deposition mask into those trenches. This is the horrendously expensive micro device that I managed to destroy as soon as I got my hand on them. And that was because instead of silicon nitride here as a bonding interface layer, they used silicon oxide, which dissolves in basic solutions. But here you can see that the detector again was buried in and then covered by the nitride as an insulating layer. A whole complex assembly of different metals that could be put on top of each other or not, depending on their adhesion strength. So this was overall a 21-step microfabrication process. I honestly wouldn't recommend to anyone, but it can be done. I just said we can make electrodes in situ as well. So here we've got someone that was a good chemist and thought that they remembered that there was the Tollens reactions where you can make silver electrodes. And you can see here that the reaction in a microfluidic device is slowly taking place, where we've got the aldehydes, two different aldehydes reacting, and you can see the point where the reagents come into place. We get a reduced silver electrode being formed, and on the next slide you can see that a little bit nicer, where we can see the different reagent channels, and we can see that The silver electrode is being formed at the boundary where these channels are. So after the removal of the reagents, we can still see that we've got a silver electrode left that's integrated into a microfluidic device. Again, very easy to do, because once we've got a microfluidic structure, we are very good dealing with fluids. We're not that good dealing with solids. If we can make our solid electrode out of liquid reagents, that makes life a whole lot easier. So the other part, next part of functional integration is adding functionality by using a carrier, using a material that you already know is going to do the job. An example, what you could do is use functionalized beads. There's a lot of beads available that have negative surface charge and are very suitable for selectively binding DNA. Why would you develop it all again if you already have got these beads ready to go and buy? These are the wheel-like structures that I talked about. If you want to pack a column, you just need to have a narrow opening and the beads will just collect in place. So you can get a chamber packed full of beads by just having a narrow opening at the outlet. Magnetic beads are great as well, because you can not only introduce them on a microchip, you can also move them around. So magnetic beads are a popular addition for integrating functionality into a microfluidic device, where the functionality is actually carried both on the outside of the bead through its surface chemistry and the magnetic core itself. So it's a dual purpose activity there. Hydrogel particles can be used to add functionality by having certain antibodies encapsulated into the hydrogels. This is a particularly nice one where they used beads in little cavities, and they applied a small negative pressure to keep all the beads in place. And this allowed them to do assays at a very small format, because they used the antibody functionalized beads to do an ELISA on, and they could very precisely define the location of all these beads, because the array that they'd created only had place for one bead in one spot. So you just flood the whole device with a bead suspension, you apply a little vacuum, each hole traps a little bead in place. You can then wash with a clean solution without beads, the beads that haven't been trapped away, and you can do a very accurate ELISA assay on the individual beads, because you know that every hole only contains one bead, but all those beads contain the antibodies supporting your ELISA assay. You can electrostatically charge the beads to get them to self-assemble into nice pillar arrays. And you can put the beads into hydrogels as well, so you can localize them through fluorescent signal when that's immobilized in. The other way we can immobilize reagents is by drying them in, attaching them to surfaces using either little spray deposition needles, inkjet printers. Not sure if you're aware, but the inkjet printers that you buy in the shop, where you can kind of hack the ink cartridges to put reagents in them. And that means that instead of printing blue or yellow ink, your printer will be printing reagent A or B. Probably there's a lot of literature out there exactly explaining how to do that with different printers from different manufacturers. If you're interested in doing a whole range of assays and you want to do it with less reagents, it may be worth looking in that with someone in engineering to see if you can hack an HP or Canon inkjet printer. A lot of this work is done with the printers that have been made for color printing at home, and then hacking the cartridges to print reagents instead of colored ink. You can stamp reagents in place, so you can make a PDMS positive structure and stick it into the material you want to stamp, and then put it carefully on the substrate. That means that you can get lines of one reagent or multiple reagents, and then allow the wet ink to dry, and that gets you a nice line of an immobilized reagent. Contact printing is kind of the same as the silicon stencil. That's an optofluidic device where you can use an optical cladding to cause reflection so that there's more light being collected here in the inside of the Whispering Gallery resonator. Here there's different channels that deposit different reagents. So this is a device that's used in two different directions. Initially, you've got a fluidic channel that goes into the screen. And you can see, imagine that the different colors are different reagents. You can then peel your PDMS off and put another structure on top. And you can then pump your channel, your liquid that you want to measure straight across. It hits the different reagent zones and it lights up or doesn't light up if the analyte of interest that your reagent zone was specific for was present in your analyte. So that's what's being done here, where you can use a microfluidic structure to selectively flow a reagent into the channel and just wait. PDMS is air permeable, so slowly but certainly the water will be evaporating and your reagent will be remaining at the bottom and can be reconstituted. We'll be looking at the reconstitution a bit later. We can actively introduce new reagents as well. So we can combine our microfluidic device with little blister packs. Contact lenses are sold in blister packs. They're pretty much similar to if you get a drug from the drugstore. They're typically packed in a blister pack and you need to push on the tablet and the aluminium foil ruptures open. You get access to your tablet. Similar idea, other than here, when the aluminium foil ruptures, you get access to your liquid reagent. So you can store your reagents in a blister in your chip, puncture it when you need it, and then the micro device fills itself with liquid reagents. Sounds very funky, a thermally actuated paraffin pump. This is a device that doesn't work at room temperature because the paraffin is a solid, but by the time the paraffin becomes a liquid, it also expands and it allows for the delivery of a reagent. We can have little glass ampules that we can break and then get the reagents to release. We can use little actuators and we can use hydrogel valves again that we can actuate using a pneumatic pump. If we talk in a little bit more detail about reagent introduction, if we want to deposit them on a small area, it may be smarter to have a straight nozzle where it's coming down than a conical one, because that allows putting two reagents in a single reservoir. And here, this is the picture that I was talking about earlier, where they deposited the reagents. Initially, with a hot needle, deposited some wax on top. Could add the sample, do some other fluidic processing, maybe some sample handling. Put a little bit of oil on top with two functions. A, to prevent any crosstalk between the two different reservoirs. And B, to prevent evaporation from the reservoirs and make sure the fluidic volumes in these chambers remain the same. Then they heat it. If you heat, the wax welts, the wax melts. So the molten wax probably, if it was not less dense as the material, it would go to the oil phase. The reagent mixed with the sample, and in this case, they did rolling circle amplification, so they could do amplification and quantify the DNA. And this is the way it looks like. You can see that there were alternating bits of green and blue and yellow. So yellow and green dye being deposited, immobilized in the wax, then the water was put on top, and you can see here the reservoirs contained the corresponding dye solution. When water was added, oil on top, you heat, you melt the paraffin, and then you get reagents back reconstituted in solution and ready to use. And the main reason people like drying in of reagents rather than storing them liquid is that they can be stored at room temperature, and we don't get a lot of problems with cold chain storage that we have for a lot of thermolabile enzymes, and we don't get any problem of growth either. So dry reagents are a much more stable way of integrating reagents than when we try to have the liquid reagents in the blister packs. So that was a large overview. So again, this morning's lectures was very much the basics. How can you make the channels? This afternoon is more of a smorgasbord, where you can have a whole range of different options depending on what your application needs and what your capabilities are. Keep in mind that you can microfabricate your structures. You can add them before bonding during assembly. You can make them in situ. So once you've got your microfabricated structure being formed, you can then add your functionality, like for example, the polymer monoliths, but also the electrodes with the tolerance reagent. You can do it during assembly. If you've got two microfluidic structures, you put a membrane in the middle, you've got a membrane integrated microfluidic device. And as they've demonstrated, going to Greenland to monitor the ice sheet, you can also add your functional components as a part of the instrument. They did that with the filter in Greenland. The MOF-based solid phase extraction cartridge that I showed has the solid phase extraction outside because they wanted to be able to deal with large volumes and only elute and use the microfluidics once their volumes were actually compatible with the microfluidic size scale. There are combined approaches, but they're increasingly rare because the more integration you've got on a chip, the harder it is to make, the more expensive it is to make. The most common combination that you can find is some liquid reagents or a chemical with the valving, because that's quite easy to automate because you just need to have the flexible valves. Any other level of integration of having electrodes for separation, electrodes for detection, a porous material for solid phase extraction, as well as a liquid handling system. At this stage, that's still really difficult to achieve, but 3D printing provides a lot more opportunities, and we'll make a quick start tomorrow, but most of it on Wednesday. We'll be looking at 3D printing as a manufacturing method, particularly from the perspective that while the sizes may be a bit bigger, bit larger, it actually provides great opportunity for functional integration. Thank you very much for listening, and this was another hour on functional integration. So core was this morning, different microfabrication approaches. This is just a little bit of a combination, what you could do with it. Any questions? No? And I go and sit out on a sunny balcony again and do some preparation for tomorrow. So just as a heads up, tomorrow we'll have a session on paper microfluidics. I'll first talk you through what's done on paper microfluidics, and then we'll do a hands-on session. So Professor Malik promised me we'll have some toys out here, and we'll actually go and draw and get creative. So you're going to do the work tomorrow, not me.
Tomorrow we will try to make some paper microfluid devices.
The other thing I've spoken with a couple of you for is for the examination on Friday, because it's going to be logistically quite hard to give you a written exam. So Professor Malik and I agreed that I'd be giving you probably on Wednesday a research article for you to read, and then we'll have a quick conversation to see if you understood what that was about. Not the nitty-gritty detail, but I'll ask questions in how was this chip made? Is that compatible with large-scale manufacturing or not? What is the separation technique used? And then we'll just have a quick, we'll split you into different groups, quick 5 minutes conversation to just see if you got the grasp what the possibilities are of microfluidics. So that research article will be coming. May have some electrophoretic separation in there because we had a strong focus on there. So the scope is that you can demonstrate me that you understand, you've got a grasp on the larger field on microfluidics without going into the very small and nitty-gritty detail. So I may ask you, why is mixing difficult in a microfluidic device? And then you say, because we've got low Reynolds number and we've got laminar flow. That's as far as I want you to know. I'm not going to say, could you please derive the equation or give me the equation for calculating the Reynolds number? I'm also not going to give you, this is my microchannel, please calculate the Reynolds number. So we're not going to go in that level of detail. I realize this, the scope of the course of my teaching will also be very broad. So it's the big picture understanding creating a little bit of familiarity with the different terms that are being used. But yeah, reasonably recent article. I liked it over a quick read. If you get the big picture, where it sits, what the benefits are, what some of the limitations are of the approach they've taken, that's all I'll be after. And you can read it on Wednesday. If you don't understand it, ask me on Thursday, so you know what to tell me back again on Friday. Does that sound like a good idea? Good. Enjoy the beautiful weather.
Thank you. Tomorrow, then please.
I'll do my best.
Yeah.